How about now? Can you hear me? Please tell me you can hear me. I'm waiting for the feedback. I'm reading all these comments. If only I would have looked down. Can you hear me? Can you hear me? Okay. I think one of the first things that I said was, I hope you can hear me, because I don't really know how the software works, but I think it works. So, I don't even know what I was saying, but I'll try to paraphrase. What was I saying? Okay, I was talking about the general idea behind these live streams. So, my wife also says she can't hear me either. That's good to know. A little late. So, okay. The purpose of these live streams is to give more details behind these projects. Right now it's the CNC chainsaw, because one of the things that I get asked all the time is, could I share more content? And the general answer is that I can, but it's extremely difficult to do. The chainsaw robot that I just did, editing the video took about 100 hours, maybe a little more than that. It's usually around 3 to 10 hours per minute of video. And sorry, let me turn off my notifications. Lots of people are telling me they couldn't hear me. Okay, we're good. So anyway, editing videos, especially nice, condensed, clear, easy to understand things, is really time consuming. And so I've been putting off any kind of second channel or anything like that just because it's so hard to do and I just don't have the time. So this is an experiment to see if I can give more information, answer questions, maybe in an even more interesting way since it's live and there can be questions. And we'll see how it goes. If you have thoughts on how it could be done better, please let me know, because I want this to be as good as possible. It is for basically all you lovely patrons, and I want to give more information, I want to talk more about the projects, and I want it to be good. So don't be shy if you have improvements. And I have some stuff that I kind of wrote down that I thought might be interesting, but I think the most interesting thing is questions that people have. I think that's just going to be more better than what I wrote down. The video was kind of all the stuff that I thought was the most interesting, so whatever's in my list is less interesting. So let's look at the chat. Now the screen is dark. Oh, whew. Okay, so let me just answer a couple of questions before I get into these things. So I don't really look at the comments for the videos because I don't know, I just don't like doing it. I'll glance through them to see if there's anything I did really wrong or if there's any feedback, but in general I don't look at it. But when I did look at the comments for this video early on, a lot of people were asking me about the lockpicking lawyer, and I think I've posted some pics of this, but I have 70 or 80% of a lock. It's a new generation, and this is the next thing I'm working on. So I'm going to be sending this to him. I've been talking to him, and I think there's a good plan. I'm actually going to send him both locks, so that we get the OG and then the new one, and that'll be really interesting. So, FYI. And okay, let's get into the chainsaw. Okay, so the John is asking about this pole saw that I made, and the question was, did I consider using a flexible drive? And the idea, as I understand it, would be like, let me see if I have one. So for the Dremel, if you guys have used these, you can have the Dremel sitting down here and then drive a little tool up top. And then the advantage of this is you can put an arbitrarily powerful motor that you don't have to lift. I did not consider that. The motor power really wasn't the problem. This motor is incredibly powerful. It's for an electric skateboard. If you think about it, this motor, you can stand on a skateboard with your full super heavy body weight, and it can start rolling you up a hill from a stop. And I think the peak output of this is about 5 horsepower. At least that's what the spec sheet says. I can't get 5 horsepower out of the wall. And torque and power, I don't think that was a problem. I actually, let me see if I have any here. I kept snapping the drive shaft. So this motor is turning a big pulley, which turns this little pulley, which speeds it up even more so that I could get it fast enough. And then there's a drive shaft right in here. I kept snapping that drive shaft. When I would overload the chain, like if I fed too hard so that it would dig into the wood, I would just snap the drive shaft. Let me see if I have one. So here's one of the drive shafts that I snapped. So this is probably about a 1/4 inch steel. Oh, that's not in focus. This is a 1/4 inch steel drive cube thingy. And this is hardened steel, which I annealed, and I tried all the different things to make it strong, and I kept snapping them. I snapped like, I think 4 of these before I was able to get the motor limiting enough that it wouldn't snap it when it was overloaded. So even if I had put a gigantic mega motor on this, the weak link was right in here. And there's not, I was trying to think if there's a way that I could fix that weak link because I was sick of breaking those drive shafts, but the way that the saw is built, there's a super complicated bevel gear in here that I can't replace, and there's just no way to make it stronger. So that's kind of the answer. Let me see if there's anything interesting else to talk about this saw since we're on the subject. So the number one question about the saw I keep getting was, did I tighten the chain? Was I running in the right direction? Was it sharp? Etc., etc. And I did check. I didn't really go into it in the video because I just didn't think it was that interesting, and the video was already really long. But I spent quite a lot of time trying to make this thing cut the log. I went through different chains. I made sure that the chain was sharp. Some people were saying new chains aren't necessarily sharp. I tried different tensions. I tried different speeds. I tried different feeds. I tried different like angles of attack. And basically, oh, I even looked at it under a high-speed camera to see what was going on. And the takeaway for me was that it just could not cut on a radius. And I even replicated it with, I don't know if you guys have ever seen these little chainsaws. The hatchet. It's a little 8-inch chainsaw. Pretty handy. It's like a Sawzall, but crazier. And this saw does the exact same thing. It has a different blade that has cutting teeth at every link. The other saw doesn't, and it still does it. And so I think what was happening, let me see if I can draw this real fast. So if I look at the chainsaw tooth up close, it's kind of shaped like this. Let me see if I can just show it on here. So here's one of the cutting teeth right here. And this is the cutting blade right here. And then this is what they call a raker. And the general idea behind this raker, at least as I understand, I'm not a chainsaw expert, but the general idea is that this keeps you from pushing the chain too far into the material, and this cutting edge taking a giant bite and then kicking the saw or doing something crazy, stalling out the motor. And so this is setting kind of your depth of cut. So if I was feeding it this direction into material, it can't cut more than this deep. And the general problem is that if I take this tooth, oops, grabbed a bit too much. and I put it around a circle, these little teeth actually, or the little rakers, become, where the heck is my tool that I need? Here it is. They become more proud. So let me show you. They stick out more when you pull it around a radius. And looking at my chain under the high speed, you can actually see this in the video that I posted. It looks as if these rakers are contacting the wood before this cutting edge even touches it. And so when I was trying to push the tip of the chainsaw into the wood, I think these were just rubbing really hard, and the cutting edge wasn't even going into the wood at all. And then that would just generate an enormous amount of heat. The small other chainsaw did the exact same thing. It happened no matter what I did with feed or speed or anything. And I'm pretty sure I saw it on the high speed. I need a zoom lens or a macro lens for the high speed, so I couldn't get totally in there to really see, but that's what I think that I saw. So the next most obvious question, which someone asked me, is why didn't I just grind down the rakers? That of course is the first thing that crossed my mind when I discovered this issue. And the general answer is that I really wanted to get this video done. I had already rewritten the software 3 times at this point, and I kind of, based on my general experience of how things go, I was pretty sure grinding down the rakers would not be the end of the issues for me trying to cut the wood. I was assuming that I would run into other heat or lifetime issues with this. One of the things that at that point I kind of understood was the fragility of these pulse saws. I think if I really wanted to do wood, I should make my own saw that's just beefier and doesn't have as little finicky metal parts that can break. And so I was just afraid that if I ground down the rakers, I would then go into saw breakage hell for like a week. And I really didn't want to go there. The general idea behind this video was actually to be a software video, because these problems of using a chainsaw I think are interesting and hard. That's actually why I did the chainsaw. It is what a lot of people have emailed me and I think posted on Discord and other places is, chainsaw is stupid, there's way better ways to cut wood. I know that. In fact, if I wanted to just get a bunch of views on YouTube, I would have not used a chainsaw. I would have used like a gouge. I don't know if you've ever seen a rotary gouge. It basically goes on the end of a die grinder, and it spins super fast, and you just push it into wood and it just cuts out like a spherical shape. And that's what people use for carving large wood stuff, or even a mill. I could put a milling head on the robot and just carve it out, and I could get super nice, super hot looking, whatever, and very easy because I wouldn't have to write the toolpaths. But then I'll write the toolpaths, not interesting, and I wanted to do some interesting software that I couldn't just download. So that's why I did the saw, and that's why I didn't do the rakers, because I wanted to just get it out there. I do want a wooden dog. Like I have someone is asking where the dog is. It is currently right here. Ugh. And it is now, I've enjoyed the foam dummy crown carrier, but this is now my official crown carrier. The reason I even have this crown is that it was I don't even remember what it was now. I had a dumb joke in a video that I didn't do. I cut it out because it was too dumb, and it involved this crown. That's why I have the crown. But I like the crown as just a accoutrement to my shop. I don't know where it's going to go. What I'm contemplating, although I don't know how to do this, so actually if anyone has expertise in doing this, I would love to hear it. I was hoping to cast this dog in another material, like do a lost foam with concrete or something like that. I think that would be pretty cool. And the foam is neat, but it would be way cooler if it was concrete or metal or something. But it is going to live somewhere. I'm very proud of this dog. There was a serious pit of despair with this project because I just could not get it to work. I didn't really even go into the challenges in the video, but I literally spent probably 10 days at that little desk trying to make this thing work. And after like 8 days, I got that horrible monkey rock dog. And I was like, this is not gonna work. But I realized the problems and I was able to get it to work, so that was great. And so this dog represents, to me, the joy of sticking with it until you get it working, and that you often can prevail if you just keep doing it even when it's really hard. So, does the foam dog have a name? No. I'm open to suggestions. I hadn't even thought about that. Do I have an anti-rebound on my chain? So the rakers that I was talking about, I think what Benjamin means when he says do I have an anti-rebound is, do I have anti-kickback? At least that's what it's called with US chainsaws. And so kickback is what I was talking about. If I stick the tip of this chainsaw into the wood, it's basically like a little wheel, and if it bites in, it can fling the chainsaw up because of the direction the chain is going. And then what really stinks with chainsaws is that when it flings it up, your face is usually the thing that's up, and so you really don't want that to happen. It's really bad. And so there's all kinds of like chainsaws with safety tips where they put a piece of sheet metal over this just so you can't do it at all. But the point of these rakers, I think, is to make that basically impossible. I think the fact that they stick out proud and the fact that I can't cut at all on the tip is a feature. I don't think that's accidental. It's so you don't stab yourself in the face. So I need a more dangerous chainsaw is the basic answer. Yeah, there's with the arm. There's not a risk for me of it kickbacking, but I was very afraid. Something I was really afraid of this whole time with this video is I was going to break the arm. This is like a bespoke. There's like 5 of them in existence. Prototype arm. That means that lifetime testing has not been completed. There's not a replacement one if I break it, and it's new, so no one even knows how it breaks. Like there could be a simple little dumb piece inside of it that could break or get fried, and I don't want to be the guy to discover that when I'm in the middle of trying to do chainsaw cutting. That was actually another reason that I didn't want to do the wood when I start to see the problems, is I was afraid I was going to overload or break the arm. And something that someone else was asking is, how strong is the robot? So it can lift, I think 8 or 10 kilograms at full speed. So that's like full extension, full speed, which is really fast. It can do 8 kilograms. It's a lot stronger than that if you're going slower and if you're not at full extension. There were some collisions that I had with the dog when I was trying to cut it. So one of the big challenges, which I actually didn't have a good answer for in my software, is that I was only checking if the chainsaw collided with the part that I was cutting. So I was doing a collision test basically for the motor and the body of the saw. But the arm can hit too. So when I'm kind of reaching to the side of the dog and cutting in the front, which it turns out was the best way, that was the way that the robot could reach the most stuff, I could hit it with the joints of the robot. And the first dog, and I hit both dogs. I was able to fix the second dog, but it just crushed it. I mean, it just like slammed the foam down and completely compressed it, and it didn't even like miss a beat. So it's definitely a lot stronger than the base specs. What if I use a square chisel chain? I don't know. I'm not really familiar with chainsaws. I'm terrified of them. The only reason I was really okay with this project is that I wasn't holding the chainsaw. I've seen how quickly things can go sideways with the chainsaw, and it's not something that you can really learn. You can't learn to use a chainsaw totally safely from doing. You have to learn it from someone else, because if you learn it through doing, you'll get hurt. And so I don't know that much about them. I know about cutting tools from milling, but for wood and fibrous things, I don't really know how the different things work together. Okay, so Kevin's asking, what's my software process look like? Okay, this is an interesting question. I don't know how many people on here are software engineers, so I'll try to just give a general overview of what he's asking. It looks like the main question is, how do I know that my code works? And do I do unit testing? So the general idea here is that when you write a bunch of code, you will write things like a math routine that will tell you if a plane collides with the model. Or you will write a routine that says, take my object and transform it in space in some way, or whatever. And the thing about the code is, does it actually do what I said that it does? And does it do what I said that it does in all cases? It's super easy to write code that sort of works, but doesn't really work. And it can become incredibly painful to figure out when you start building layers and layers and layers of things on top of things. So if I wrote a routine that is testing if a plane collides with the thing, I might have 10 layers on top of that are using that to do all kinds of different operations. And if that is subtly broken, I can just get a totally insane result, and it's extremely unclear why my result is insane, and it can take vast amounts of time to figure out that that specific little piece of math is what doesn't work. And so what a lot of software engineers say is a good thing to do, and I generally agree usually, is that when you write one of these math tests or math routines or whatever it is, it's not just for math, but in my case it's usually math. You write a set of tests that run the routine against all different kinds of inputs and confirm that the output of it is what you want and that it's doing the right thing. And there's all different sorts of schemes. Some people will do what's called test-driven development, where they write tests before they even write their code. They say, this is what I want out, and I'm gonna write code that gives me those things. And I don't go that far, but I do write unit tests, because I've been burned so many times by small pieces of functionality not working and it taking me hours or days to figure out. So for anything that is an important math routine, I will write tests that I can run. They're also useful to confirm that you didn't break something when you change stuff. So like if I want to add more functionality to a routine, I want to make sure I didn't just break it when I optimized it or whatever. And so unit tests are really useful for that as well. I do use those. I don't do them as much for high-level application stuff. So, for example, the thing that generates all the cuts, I don't generally write unit tests for that. That's like the top-level kind of application. And the reason I don't is that my code typically changes too fast, and I don't know what I want up front. It's not clearly specifiable like a math routine. And so for that stuff, I don't. And I guess my general, oh wow, there's lots and lots of, I'll read the comments in a minute. My general workflow for writing software is that I'll usually start not in the editor at all. I'll try to draw out what I want to do in my general approach for doing the thing. So for this chainsaw problem, I talked about the apple peeler algorithm in the video. Before I wrote any code, I sat down and drew out kind of like a flow chart of the various processing steps and what I need at each step. So I'm going to start with a model that is like an STL. It's a bunch of triangles. And then I'm going to take a slice of that model, which will give me a contour. And I'm going to take that contour. I'm going to use some kind of polygon library to clean up the polygons. There's actually a bunch of problems related to that, polygons that self-intersect and things like that. Then I'm going to do my Minkowski difference and on to having it, how to render it and so on. I use that to basically as a guide when I'm starting to build the application so that I can get roughly the right layout for the code files and architecture and other things. It's generally, in my experience, more right when I do it that way than when I just go in and start writing code. And the other thing that I usually end up doing, this isn't explicitly planned, but I almost always end up rewriting the code. So I will go in and I'll just, as quickly as possible, bang out as much of the code as I can and get it mostly working. Usually in the process of doing that, the code will evolve continuously to the point where it is so nasty that it's too hard to work with and brittle. So I'll usually get it working, and then I'll either rewrite or I'll do what's called a refactor, where you essentially just you don't totally rewrite, but you will reorganize the code in place and clean things up so that it looks nicer and move things around between files and so on. And then it's still usually a mess, and I still usually continually edit it as I go. Usually for these types of projects, I don't actually know, and I don't know how I'm going to solve it totally, and there's all kinds of roadblocks I run into, so I end up adding more and more stuff, and it gets quite messy. But that's my general workflow. A lot of people ask me if I can share the code. So far my answer is no. And one of the big reasons is that when I get done with this code, it is a mess, because I'm doing open heart surgery on it continuously until it works. I try to put the thought in up front, but it ends up being a mess. And I think it is not actually useful for people to spend a lot of time trying to understand. My personal pride, I don't want to share that kind of code. I want to put the time into making it more legible, more readable with comments so that people can actually learn from it. And I just don't have the time. So that's why it's been no so far. All right, we got some strategies. Oh yeah, I was curious if people, so I'm going to read through this strategy in a second, but something that people ask a lot is, or that I've been asked, not asked a lot, but something that people have sent me emails and proposed different algorithms for doing this cutting for the model. And one of the most interesting things I think when you have a strategy is, how can I break it? And that is one of the hardest things with these algorithms, especially for complex arbitrary geometry. So I wasn't just trying to make this robot work with just a single thing. I was hopefully able to take any mesh in and then cut it. So the inputs are arbitrary. And so the interesting thing is, for a proposed strategy, can I come up with an input that will break that strategy? And when you're doing stuff like continuously cutting away material from a shape, you get so many different cases appearing that you wouldn't even think of, like weird geometry and strange stuff, that it makes it really hard to figure out. So Cuthbert is asking my thoughts on a strategy where I start with my object, and then I compute a cylinder that will enclose the object. I assume when you say the smallest cylinder, you mean aligned to an axis, because you can imagine that, I don't have a good cylinder around here, but the right cylinder, the smallest possible cylinder, might be arbitrarily oriented. So that's a little bit tricky even in itself. And then reduce the size of the cylinder, and then compute wedges to just do the shapes that are in the inch, that basically the space between the original cylinder and the reduced size cylinder, and then repeat that until you're complete. And so I guess I can break this down a little bit. That doesn't really help that much with the problem. For one, I guess I'll do the first thing that I was talking about, which is how you might break that. So imagine that I have a model that's 2 cylinders. I think that the reducing cylinder isn't all that meaningful for the 2 cylinders, because you will basically in 1 or 2 steps expose the entire models, and then all the remaining steps are just free space. So it didn't actually really help you all that much. But the bigger problem with this algorithm is just the sheer complexity from the number of options. So in my video I talked about how it would take my computer 1,000 years just to count the possibilities. What I didn't say is that that is for one position in space. So it would take it 1,000 years to count the number of possible cuts that I could do for just a single position. And it's actually infinite. So the way that I did that math is I said, if I want to test, say I have a wedge in space at a point, centered at some point, and I can rotate that wedge about all 3 axes. I can also make it longer. I can change the angles, or the angle of the wedge itself. And then if I sample that basically at like 1/2 degree increments for all the different measurements, you get like 1,000 years. But that's not actually even the right answer, because there's the possible angles, or it's a real number, so there's infinite angles that I could test at. So that's just a sampling. When you then do that for every point in space, you get if I do the same thing, so if I divide my model into a grid of millimeter points in space, the number of points that I can test at is basically the cube of the linear dimension, because the volume of the space is length times width times height. And so if it's cubing of linear dimension. So that turns my 1,000 years into like 1,000,000 years right off the bat. And so even if you do the cylinder thing where you cut out 90% of the possible points, it's still intractable. And then the other sort of difficulty with that approach is that although you're only looking at the first inch that you could cut, you still have to consider the entire model, because the saw will hit it. So the collision detection was actually the thing that was the most expensive for this software. Because basically if you don't know how collision detection works in video games and other things, the general idea is that you have to, I'm trying to think of like the best way to describe this without using the iPad. So imagine that I have a set of triangles that represents a model, or a set of points. That makes it easier to talk about. So I have a set of points that represent the boundary of a part. If I want to know if this saw collides with that model, what I might do is represent this as a plane, like the blade, and go through every single point that represents the model and see if this plane, if a point lies on each side of it. If that's true, then it must be inside the thing that I'm looking at. And that's really expensive, because I have to go through every single point and test it. So if I'm testing a million orientations, I have to do that a million times to see if it's colliding, and it gets super, super expensive to do. There's lots of tricks to test less points and other things, but in general it's pretty expensive. And that was the main driver of the computation time for my algorithm. And so the question is if this is fundamentally a traveling salesman problem. That's a great question. It's hard to prove. I'm not going to go into NP-complete problems, but in general, there's a set of problems that are they're called NP-complete, and the idea is that you can't solve them quickly. NP stands for non-polynomial, which means it's like an exponential kind of solution where it just takes forever. And there's an enormous amount of research into this, because if you can find a way to solve these problems, you like break encryption and all kinds of things. If you want to look into it, it's pretty interesting. And so the traveling salesman problem is one of these NP-complete problems that is really, really difficult to solve. I think, and so the assertion is this is like a traveling salesman problem. I think that this is harder than the traveling salesman problem. So I'm going to attempt to give an example. I don't know how well this is going to go. I haven't done this math in quite a while, but let me give it a try. So there's a set of problems where you are basically saying, if I'm here, what is the shortest path to get over here? And I really don't know if I'm going to be able to do this justice, but hopefully I can get my point across. What you do, there's all kinds of different approaches to solving this problem, and it kind of depends on what you want. If you're moving a robot, you might want a path that goes kind of through the middle. If I just want the absolute shortest, it might be like this. And there's a set of algorithms where I can give geometry and find the shortest path between the 2 points. If I'm doing it in 2D, this is a well understood problem that I can solve. I can get the best answer, and I can do it in what they call polynomial time. If I take this problem and I go into 3D, it no longer works. I'm not really going to be able to draw it, but the basic gist is that when I'm in 2D, when I'm in a plane, I know that the shortest path is going to touch the objects that are in my way. That's not true in 3D. So in 3D, I'll leave this as an exercise to the reader. The shortest path might actually kind of go to some random point in space and then cut across to get through a thing, and that might actually be the shortest path. And because of this fact, if I need to do the thing where I test all the possibilities, there's essentially infinite points in space that I could inflect about to get there on the shortest path. And so it becomes completely unsolvable. And this is a different class. This is harder than the traveling salesman problem. It's called NP hard rather than NP complete. And it's even harder than NP complete. I think that the problem that I'm trying to solve is actually NP hard, because if you look at what I have to figure out with the saw, it's very similar. So if I have some shape like this that I'm trying to find the best cut for, the actual cut is not necessarily touching the model at the inflection point of the cut. It can be anywhere in space. In fact, many times the best cut is not touching the model there. And the number of possibilities, I think, grows similarly to this problem that I know is NP hard. And so I think it's like totally unsolvable. I had a guy emailed me and said he thinks he can solve it, so I said go for it. I'd love to see the answer, like to actually solve the optimum one. So all that I was trying to do, like the most of the work for this problem was trying to find an approximation. And that's honestly what makes it kind of hard, because I can formulate relatively easily a routine that will find the best cut. The problem is, if I try to find the best cut, it will take forever. Like the computer will never, it just doesn't have enough processing power to do it in any finite amount of time. When I try to find a reasonable cut, that's actually harder, because I have to define what a reasonable cut is. What is a reasonable cut? And what makes a cut better than another cut, and good enough, and so on. And that actually was pretty hard, because you're trying to find something good enough, and you're trying to find a way to like go through the possibilities in a quick enough way and not miss the great cut, and so on. So it's just hard. It ends up being what people call heuristics. So yeah, that's the general idea. I don't know if that really answers your question. Yeah, pulse saws kind of suck. I agree. See what other questions we got. Yeah, what if I just bought the chain and made everything else custom? That is a thing that crossed my mind. In fact, my inclination when I ran into all these problems with the chain is like, all right, I need to build a chainsaw. This is gonna be fun. But I restrained myself, because I knew that was sort of a tangent for the video and the project. So yeah, there's a lot I can do to improve the chainsaw. I'm sort of torn whether I should do. I can put a lot more time into trying to make the chainsaw work. I know that it's the wrong tool, and so I'm not sure if I just want a great dog or bear or whatever, or if I want to get a good dog with a chainsaw. I'm not sure. And I'm kind of also torn, because there's a lot of other stuff I want to do with the saw, or with the robot. It's just such a cool thing, and if people have suggestions, I would love to hear them. When I asked on Twitter, people were talking about having it paint and do some other cool stuff, which I think would be a really interesting thing to do. And so I'm not sure. I don't know if I want to put a lot more time into trying to make it chainsaw when I can put even more time into making it do something totally new. Let's see, what else? So I didn't really talk about the electronics at all in the video. I don't know if other people are seeing this, but the supply chain for electronics and electronic adjacent things right now is just awful. I could not get a power supply on any reasonable lead time to power this motor. And it's kind of a weird situation, because these motors and the speed controllers for them, they are designed for batteries. They're not designed to be run off of a wall. And they have a couple big problems, which is that, one, they often ask for an enormous amount of current, which is sometimes hard to do with these DC power supplies. And then they do regeneration. So when you try to slow down with an electric skateboard, it uses the motor like a generator to basically slow the board down and then put energy back into the batteries to recharge them. So you get more range, which is great. It's not great when you try to put a bunch of energy back into a power supply, because they just don't like that. There's nowhere for the energy to go, generally. Like it either has to have some kind of like heating element in there that it'll burn that energy up and heat up, or try to dump it back into the mains somehow, and it's just not something that they expect. So that was kind of a problem. And what I started to do So what I did is I bought 3 power supplies, 3 very cheap 12-volt power supplies, and I put them in series to get 36 volts. And because it was the only thing that I could find, and I needed 36 volts. And then what I was going to build, I have all the parts to do it, but I was able to avoid it, is what's called a clamp circuit. And so the idea behind a clamp circuit is you have an arrangement of electrical switches that will turn on if the voltage goes above a certain limit. So when the motor's regenerating, the voltage goes up. That's just how it works. And so what will happen is if the voltage goes beyond a certain limit, it will turn on a circuit that will divert the power through a big resistor. And so if the motor's regenerating, it'll just turn on and then it'll burn a bunch of heat through a resistor. And then when the voltage comes back down, it'll turn off. And so I had a bunch of power resistors and other things to do this, but the speed control I was using has a lot of different configurations where you can control how much it regenerates and other things. And I was able to get it regenerating low enough that the power supply could handle it. I wasn't sure if I was going to be able to do that, but I could get it working. And you can't turn it off completely. It just won't let you. It doesn't work. So thankfully I was able to get that working. And it's pretty funny. If you look at this general problem of not just regeneration, but energy in a motor is a big problem in electronics. Like if you look at certain mills, you have the spindle going super fast, and it's not just the motor turning, there's a big hunk of metal hanging off the end of it, which has a bunch of energy stored in it because you're spinning it really fast, a bunch of kinetic energy. And so if you want to go from like 10,000 RPM to 0 really fast, which they often want to do, you have to take that energy and do something with it. You can't just go to 0. You have to stop it, like brakes on a car. And so if you, like Haas mills, it's really funny. If you look at the back of them, there's a stove. There's literally like a stove on the back of it. It's a heating element, like one of those coil heating elements from a cheap stove inside of a little sheet metal box. And they just like dump all the energy from the spindle into that and it gets red hot. And that's how they stop the spindle. So really cool and really interesting set of problems. Let's see what else people are asking. Did I consider using a block of ice? A bunch of people suggested this. I think it's a fantastic idea. The reason I'm afraid of doing it is that there's so much electronics exposed. Like the robot itself, it's full of electronics. Then you have all the chainsaw driver stuff on the end. And if I wanted to do a block of ice, I would really need to enclose everything, which there's ways to do it. People have robots doing all kinds of extremely dirty stuff. They'll like basically put a bag around the robot and that works pretty well. But I was not really wanting to open that can of worms, so I just didn't do it. But I think it would be really funny. I think it would work really well. I think it would be super cool looking. It might be a good winter project when it's 85 Fahrenheit for all the English people here. So my ice would melt really fast. Does anyone know why there's a national chip shortage? I guess this is a bit of a tangent, but I haven't heard a good answer for that. How much the chainsaw model did I do in CAD? I modeled everything. So let me pull this thing apart so I can show you what I did. I don't think I showed any of this. So when I'm designing parts like this, my goal is to minimize the amount of time I spend machining because it just takes so long. And so and then my second goal is I want to make it as easy to modify as possible because I usually get it wrong. And if it's a super intricate design that's challenging to work with, then it can really add a lot of time to the project. This was one of the difficulties of the pool cue, is that it was so miniaturized because I wanted it to be small like a pool cue. It was just impossible to change. And there are some things that I wanted to change about it to make it more accurate, but I just couldn't do it. So let's see. So here's the actual business end. And the way that this thing works is you have the drive shaft, a little piece here that I just really two CNC'd pieces. There's this thing that holds the bearings, and then there's this mount. It's all cored out because I wanted it to be light. I definitely went overboard on this, but it's free to do with the CNC machine, so it doesn't really matter. This whole thing was machined in it's just all one-sided, so I could just machine it in one, and then the same thing with this thing, it was just machined as one. And then I have this pulley that I had to make because I just couldn't find one that would work, and that was also done in one operation. And so the thing that happens, the thing that causes a lot of problems for me is I can't actually assemble the thing. So it's very easy to design a thing that isn't assemblable, and that happens more often than I would like to admit. So when I CAD a thing, I model everything. I model the chainsaw. I didn't model the teeth of the chainsaw and stuff like that, but I measured and digitized the whole thing. And then same thing for the motors. I was able to actually find this motor on GrabCAD. If you do CAD, you don't know about GrabCAD, you should know about GrabCAD. Servos, motors, bearings, you can find CAD for like an enormous amount of things, especially the common hobby parts. And then the other good resource is McMaster. They have 3D models for most of their stuff too. So you can save a bunch of work by doing that. But I model everything because I was really concerned about assemblability, especially with this drive shaft. I originally had a whatever you call those. It doesn't matter. The way it was assembled, there was nested bearings with clips and things that can be difficult to assemble. And then I was really concerned about hitting the robot. So I had a CAD model of the robot from Tormach. They gave me the CAD, thankfully. And this was actually one of the really, really, really hard things to figure out about this project is where should the log be? Because you can imagine that I can put the log further out, and then I have more space to kind of get in from the side, but then I can't really get all the way above it. I can make it lower, and then I can really get above it, but it's harder to get to the bottom. And the robot, the way that it moves, like it was really challenging to figure out where the sweet spot was for the log. And so that's the other reason I CAD'd everything in this case, because I wanted to be able to play around with it digitally before I bolted a stand to my floor and all that stuff. So long answer, but that's the general idea. And then I do parametric as much as I can, kind of like the CAD. Things start with good intentions and they're pretty clean. Towards the end, they get worse because I keep changing things and breaking my original intent. So the parametricness doesn't work so much. But like the wall basketball hoop is all parametric just because it was a lot easier to do it that way. How do I control the robot? So there's two ways of controlling the robot. The really awesome thing about this specific robot is that it just has a Python programming interface. It uses ROS. And so you can just connect to it with Python and do whatever you want to do. They provide an interface for you, which is what I was using. Rather than interfacing with ROS directly, there were some reasons why I didn't do that. But the general interface is you can either say, I want to move to this point in space. So you could say like, the robot's here, I want it to go here in a straight line, or I want it to go here around a circular path or whatever. So there's all those kinds of moves. And then the other way that you can control the robot is you can stream it a series of coordinates. So if you give it the straight line move, you can't really control the velocity. Like you can give it just a velocity. But if I want that move to like start slowly ramp up in speed and come down in a very specific way. I can't control it in that way with those types of moves. And so they have the ability to stream it a series of points, kind of like at 20 frames per second or something, or even like faster than that. And then it'll just execute those. And I used both methods. I found the series of points better because I could more easily vet the toolpath because I knew exactly what it was doing ahead of time. And that was another challenge of this problem, or this project, was it was really easy to command the robot to do a move that it couldn't solve. And so you might be over here and you say, go over here, which you're pretty sure you can get there, but the robot's just like, I can't do that, sorry. And that was one of the biggest sources of wasted time for me, was just debugging. There's so many cases of these where I just couldn't move to where I want it to go, and getting to the bottom of that. And you know, it's beta software. Like their first release of the software was like a few weeks before I did this, and so I ran into lots of problems, and they were very helpful, and they fixed lots of problems, and they gave me features specifically just for me to do this, so very helpful. But that's kind of the name of the game with beta software. So it looks like the reason there's a chip shortage is all of the reasons. That's pretty funny. Everyone's sitting at home wanting updated computer setups. When the pandemic started, and I saw that they were going to be giving, in the US, they're going to be giving everyone a check to stimulate the economy, I thought, I bet a lot of people are going to be buying computers, especially GPUs. So I upgraded my computer because I needed to, and thank goodness, because you can't now. So that was a good call. What is Tormach's intended use for this robot? They're very interested in the idea of, I don't know what the right term for it is, but basically a person running a shop, making parts, like a small business. And so one of the things that they're interested in is machine tending. So say you have a Tormach mill, the main cost of running it is just your time, standing there and switching parts out and so on. So if you can have an arm that you can just put in front of the machine, and it's really easy to get it putting parts in and out of the mill, you can do kind of what people call lights out machining, where you don't have to be there, although you probably should be there. You should at least have a baby monitor, but you can turn the machine on and say go, and then come back to like a bucket of parts, and it can save you a bunch of time and money. So that's one thing that they're interested in. And then there's a bunch of other use cases for these types of arms. I know there's been a lot of different industries that have shown interest as they've talked about the arm and the pricing and the software integration that it has. I suspect, I don't know if this is true, but I suspect there's going to be a lot of people who want to get one of these for making videos. It is a really great way to move a camera. That's one of the things that I want to experiment with. I feel like everyone who makes YouTube videos in the maker space always builds some kind of like camera slider or moving thing. And of course, the thing I've always wanted to build is a camera robot. And I have a robot, I can attach a camera to it. So I'll probably do that. And I think there might be some demand for that if people use it successfully. The next big tool, I just got a tool I haven't even set up. It's a selective laser sintering machine. It's the Formlabs Fuse 1, and it sinters. It's a 3D printer that sinters parts out of nylon powder, and it's going to be great because these parts they're just phenomenal. I've worked with them a lot because I worked at that company. They're super great impact strength, really strong, and they have really good elongation before they break. So they're really, really good for functional things. So I just got that, and it's kind of hard to think about other tools when I haven't even set up that tool. And the next tool that I want, although the only way I'll ever get is if I can find a way to work a deal with a company, just because they're way too expensive. But what I really, really want is a fiber laser cutter or a water jet. I would take either. So far, no one wants to play ball with me, but that's what I would like to get. The reason for it is that I have the plasma cutter, which is kind of like a poor man's water jet or poor man's fiber laser cutter, but I keep running into designs where I want to make really fine little sheet metal parts with flexures and other things, and so it would be really useful to have one of those machines. Totally superfluous, but if I could get one, I would take one. And then does the Tormach, I mean that Tormach has a tool carousel. I don't know which Tormach you're talking about. I have there's the robot arm, there's the router, there's that, and then I have the plasma cutter. But the 1100MX, the CNC machine has a tool changer. What is the first tool? We're getting a bit off topic, but I'll answer the questions. What's the first tool I would replace after natural disaster? Probably the chop saw, because that's like I assume there's a natural disaster, I need benches and I need all kinds of stuff. The chop saw is actually one of the very first power tools that I bought because it's so useful. Like making this bench, making shelves, whatever. Really, really, really useful. I have not seen the surgery robot that Michael Reeves put a camera on. I assume that he uses it as a camera mover thingy, kind of like this robot. Sounds interesting. I would love suggestions for what I could do with this arm. There's so many cool things. One thing I was thinking would be really fun would be it's kind of dumb, but I think it'd be really cool to see how accurately I could do something like shoot a bow. Like, could I attach for a bow and arrow, could I have it fire a bow and like just hit bullseyes all day long? That would be kind of fun. And then I also think there's a lot of interesting art opportunities with it. So it can move within a pretty big volume anywhere, and it's all programmatic. So you can imagine attaching lights to it. There's all sorts of really interesting long exposure stuff you can do. And so, I don't know. There's a lot of stuff I'm thinking about that I would be interested in doing with it, but no, I haven't thought about it enough to have a clear next step. It's not fast enough to play ping pong. If you look online, there are videos of ping pong playing robots. There's one with a robot arm, which is completely fake. It's just a marketing video. And then there's one that's real, it's actually a Delta bot. So if you aren't familiar with the various kind of types of robots, a Delta bot is where you have basically 3 rods that come together, and you can move the ends of the rods independently, and then that defines where the thing is in space. And Delta bots are super fast. If you look up all the videos of how it's made in factories when they're like picking up Twinkies and moving them from one assembly line to another, it's usually a Delta bot going at like the speed of light. They can move so fast because they're super light. And so there's a Delta bot, ping pong bot that you can find that actually works and is really good. And I think that's what it actually takes to do it well. These robot arms, maybe to play against a kid or something, but not at any level that's good. Domino 3D pyramids. Have it shoot an apple off my head. Oh my gosh, that is That is a really good idea, but also not a great... My concern with those types of things is that I'm going to inspire, like, even if I found a way to definitely do it safe, like imagine that I shoot an apple off my head and I designed some kind of barrier. Like, you could imagine I might have a piece of sheet metal out in space in front of my head that if something went wrong with the robot and it shot down, it couldn't actually hit my face. It would like act like a shield. Say I did something like that and it was pretty safe. My concern with doing something like that is that someone will try to imitate it and they don't know what they're doing, and then they shoot themselves in the face with an arrow. And so I've avoided generally doing anything like that, even if it would be super sweet, because I'm afraid of copycats. And this is one of my concerns with the powder actuated bat and other things, is that I would inspire people to do similar things, and I've seen a couple of people doing similar things, and for that reason I don't think I'm going to do any more powder actuated stuff, because it is extremely dangerous and it's really, really easy to shrapnel an important vein and die. And so I don't want that happening to anyone. It is a really good idea though to shoot the arrow off the head. I hadn't even thought about that. Let me see if there's anything else to talk about. Does anyone else have any other things they'd like to know about this robot? Questions that you had watching the video or whatever? I would love to answer it if you do. I guess one other little thing that I could talk about is the one other aspect of the software, which is something I should have done. I put it off because I didn't want to deal with it. But the computation that I was doing, it was basically, it was computing kind of the same thing a zillion times. So like when I'm trying to figure out if the saw collides with the model, I'm basically doing a pretty simple computation of, for all the things in the model, do they intersect the saw? So I'll run like thousands and thousands of computations that are basically the same, they're just different points in the model that I'm testing. And so these computations were very, very parallelizable. Basically, that I can break the problem down into a bunch of little problems, and I could send them to, say, 1,000 computers, compute them independently, and then reassemble the result to get my answer. And so if I had 1,000 computers, I could just distribute it and do it super fast. And then if you may or may not be familiar with how GPUs work in computers, they basically are this. They have thousands of cores. So like a normal CPU will have like 8 cores or 4 cores, something like that. GPUs have thousands of simple cores. And so you can basically do exactly what I said. You can send these simple problems to it and it'll massively parallelize them and process them all at the same time rather than in series, which is what happens on the CPU. And if I had taken advantage of the GPU, I could have made this massively faster. I've done GPU programming in the past. It can be challenging. It's very hard to debug sometimes. So I was putting it off, but that's what I should have done. If I was trying to make this fast and for some reason I was trying to make a product around this, that's what I would do. Just as an aside. Do I have a 3D printer? Yeah, I have a Form 3 and a Fuse 1 and an Ender. I worked at Formlabs, so my job was designing those printers for 8 years. And they're really good. The arm can throw the basketball, probably. The arm cannot do continuous unlimited rotations. I wish it could, but it can't. Yeah, hooking up to I was hoping to get the arm before I finished the pull table so I could hook it up. I just didn't have it in time, but that's a really good idea. And I think I get to keep the arm. I need to check in on that, but I think it's mine. So that's the other reason I don't want to break it. I would be ashamed to break such a sweet arm the first time I use it. All right, well, give people a minute more if you have any more questions. I don't know if this is useful or good. I think something that I could do that would have made it better, I didn't think about it, is collect the questions ahead of time. So if I do this again, if people liked it, I think I'll do that next time. So I'll post the video and then I'll post a thing that will collect Q&A stuff, and then I'll have a list that people can vote on, and it will be vetted, and it'll be like top to bottom the most interesting things. And I think that'll be better. So dance choreography. Problem is I can't dance at all. There's people ask me what I can't do. I can't sing and I can't dance. So anything involving those two things are a no-go for the channel. I don't know how expensive the arm is. It's probably like $10,000 to $20,000 would be my guess. I think that's about right. Which is expensive. I would never be able to buy an arm like that, but as far as robot arms go, it's not crazy. I think that's kind of typical. So, alrighty. I hope you guys like this. Like I said, I'm going to try to refine the format. I hope that this can become a useful way for me to share more details and teach people more stuff and so on. So thanks for robot arm haircut. Yeah, sorry, I'm a little ADD here. Thanks for tuning in. Hope you liked it, and have a good day. And I'll be posting more stuff that I do with the robot in Discord. If you're not in the Discord, that's where most of the action is. I post on Patreon occasionally, but I post in Discord pretty frequently. So if you want to like make suggestions and see what's going on, that's the place to be. So have a good whatever time zone you're in. For me, it's the afternoon, and I'll see you later.